how to get there. We have now two presentations. First one is from Max, two presentations from non-Sun employees. First one is from Max Bruning. I know him basically as the kernel guy. Met him last year in St. Petersburg, where he gave a speech which was really amazing about how to do kernel debugging and how to track down problems there. Now he's talking about a completely different topic, about ZFS and about ZFS debugging. You're very... No, not really? Well, okay, you would tell what the talk is about. We are very keen on what you are telling us. Okay, Max.
Okay, thanks. Okay, so what I'm going to do is use a modified mdb and a modified zdb, or zdb if you prefer, to walk the data in a ZFS file system on disk. And the reason I'm doing this, well, maybe it could be used for recovering problems, but that's not why I'm doing it. I'm doing it because I wanted to learn what ZFS actually looked like, so that when I teach classes and I teach internals classes, I could talk about what's actually there instead of basically reading the on-disk format specification that you can find on Open Solaris. So that's what I'm going to be doing, and hopefully I don't lose everyone or put everyone to sleep. I'm going to basically do an overview, a very short overview of some of the data structures that are on the disk, and then basically a data walk. I'm going to basically take the path name to a file. Starting at the uberblock, I'm going to get to the data of the file, all in 25 simple steps. And I've left some stuff out. And I will take a short look at mirrors and child data sets and snapshots. My technique does not work with RAID. And I have an idea of why it doesn't work, but I'm not sure. Well, right now I have no plans on figuring out how to get around that. But I'll talk more about that at the end. So I'll present some conclusions and future work that I might get around to, and the list of references, which I think are not complete. Well, I'm sure they're not complete, but that's where we're going. So, okay, so as far as what's on the disk, everything starts with the uberblock, which is the equivalent of a superblock as far as ZFS is concerned. And the uberblock contains in it, one of the things it contains in it is something called a block pointer. And in fact, most of the data is found by using block pointers. And the block pointer contains a description. What is the data? It contains the location. Where is the data on the disk? And it contains size information. The dnode, there's an in-memory copy of a dnode when you access a file. The dnode on the disk is called a dnode phys-t, and most of the dnodes are located on the disk in arrays. Now, these arrays are not necessarily, in fact, generally not contiguous on the disk. And this data structure, almost everything in a ZFS file system is described by a dnode. One of the things that a dnode will refer to is something called a ZAP object. This is the ZFS attribute processor. And this basically is name-value pairs. So what's in a ZAP? Well, the main thing that's in a ZAP are directory entries. Okay, so if you have a directory foo, and in foo you've got files A, B, and C, the ZAP object will have A, B, and C, and the names A, B, and C, and it will also have for each name something called an object ID, which is the equivalent of an I number. And it turns out object IDs are actually just indexes into the dnode fizz arrays that you can find on the disk. Also in the dnode is something called a bonus buffer, and not all dnodes use the bonus buffer. Maybe the main piece of information you can get in a bonus buffer is something called a Z-node. And the Z-node is basically attributes about a file. So size, timestamps, the stuff you would see with ls-l. All right, so that's a very brief summary of the data structures. And here is the simple picture of everything. So all this stuff is on the disk. And for those of you who think ZFS, it's really aggressive on its caching and it likes memory, look at this picture and you really want this stuff in memory. We don't want to go to the disk to access a particular file and have to go through all this stuff every time. So we start with the uberblock, and in the uberblock there is a block pointer which contains the location of something called an object set phys-t, and this is for something called the MetaObject Set. So ZFS basically treats everything as objects, and the object set phys-t, the MetaObject Set, is an object that defines all of the other objects that in turn define file system objects. Which actually, if we go through this, you'll see this. One of the problems I had, I've been trying to actually figure this, the layout on the disk, I've been trying to understand this for about 1.5 years, maybe longer. And one of the problems I ran into is that basically almost everything on this diagram is compressed. So I would go to the disk location specified by the block pointer and get what was there, and I couldn't make any sense of it. And then this light bulb went on. Maybe it's compressed, and oh, it's all there. Everything is there. But it took me a while to figure this out. The other issue that I've run into is there's 2 places up here where it says indirect blocks, and the indirect blocks can go 6 or 7 levels deep. So you start with one, you go to the next, you go to the next, you go to the next. You're basically, you make a mistake anywhere in here and you don't realize it until you've gone through the whole walk and you don't get the correct data. So the object set phys-t, the MetaObject Set, may or may not have a block pointer which is for indirect blocks. It may, on the file system that I did this on initially, the file system was very small, and the object set phys-t, the MetaObject Set, the MOS, basically the block pointer pointed directly to the MetaObject Set, the dnode array. I have another ZFS file system on my laptop on a USB drive, and this is about 140 gig, and there's a couple levels of indirection. So basically we go from the object set, the MOS object set, to the dnode array, and if you dump out the dnode array, the first entry, entry 0 or object ID 0, is not used. And for the MetaObject Set, object ID 1 is for something called an object directory. Now the object directory has a block pointer in it that gives you a ZAP object, and the ZAP object has maybe 3 or 4 name value pairs. One of the name value pairs is something called the root data set. And the object ID that gives you, at least on the ZFS file systems I've done this with, the object ID is object ID 2. So the third entry out of the dnode array is object ID 2, and this is a DSL directory. And this contains a bonus buffer. Now, it does not contain a block pointer. It contains a bonus buffer, so it's embedded in the dn type equals 0xc dnode, and this bonus buffer is a DSL dir phys t, dataset L, I don't know what L is, don't remember, but a directory phys t object, and again an object ID, and that takes you to this DSL dataset dnode, and the DSL dataset dnode contains a block pointer which gives you a another object set phys t. Now, at this level, you can have multiple object set phys t's if you have Snapshot, if you have child data sets. So you've got a file system / ZFS, and under that you've got /ZFS / new file system, where new file system is another ZFS file system. Each one of those file systems will have this objset phys t that's kind of in the middle of the diagram, the one that's labeled file system underneath. It's just this one right here, which, well, I can see it fine, but if you're in the back of the room, I don't know if you can see this little red thing. But at any rate, this guy here, every file system I've looked at, there are 6 levels of indirection to get to this dnode phys array, which is all file system objects. Again, in this dnode phys array, the first entry isn't used. The second entry is something called a master node. And the master node contains a block pointer of a ZAP object, which contains a name value pair for something called root, which is going to take me to the root directory of the file system. So I go from the master node ZAP object to the root directory dnode, and the root directory dnode has a znode phys t, which contains information about the root directory, timestamps, ownership, that sort of thing. And it also contains a ZAP object, which contains name value pairs for the root of the file system. And so what I basically do is find the name of the file that I'm looking for in the ZAP object, and this takes me to, gives me another object ID, which is for plain files. Again, this dnode has a znode, which has information about that particular file. Again, ownership, timestamps, size, and it also contains a block pointer, which may or may not use indirect blocks to actually get to the file data. So what I'm going to be doing here is using ZDB and MDB and going back and forth and walking all of these data structures. So, and I've done dry runs of this talk maybe 6 or 7 times now. And in fact, last week I think I was in Russia and did a dry run that I did in 10 minutes because I had a plane to catch. So I skipped almost all of the stuff with MDB and just went to the end. But I have time to do some of it now, and when everyone's falling asleep, we'll skip to the end. But we go on. Okay, so what did I do to actually be able to do what I'm going to do here? I've made modifications to MDB to allow me to use basically : print on a raw disk or raw data. And I've actually found that I can not only can I look at ZFS this way, but I can also do things like look at UFS files. So I can go to, I can say 2000 : print struct superblock, or whatever the name is of the superblock, and it shows me the superblock from the disk. And I've written some a couple of walkers and some D commands so that now with UFS I can basically say, here's an I number, give me the inode. I can walk directory entries. It's really easy to do. ZFS took a lot longer to figure out. So basically the MDB modification is I load the kernel CTF information. So this is basically It's kind of extended symbol table information. It contains information about structure members so that you can use : print and print out data structures. And normally, if you try to do : print on a raw disk or a raw file, it will, the : print will fail because it doesn't have the CTF information. And so what I do is basically load the CTF information for the running kernel so that I can use : print. And I wrote a little dmod, which is an mdb module that allows you to use : block pointer, which gives you a nice formatted listing of block pointer entries with binary files. And for ZDB, one of the commands to ZDB is in -uppercase R, which allows you to read a block on the disk. And there is a comment in the source code that there's various options to ZDB, various flags, and one of the flags is decompress. And next to that flag, there's a little star. And if you go to the end of the comment, next to the star, it says, not yet implemented. So I implemented it. Basically, the stuff that I've added to ZDB shows up right here, the D, LZJB, and L size. So with ZDB, you can specify a pool, a ZFS pool, a vdev, a location that you get from another block pointer. This will be a location on the disk, a physical size, which is the size on the disk, and then the options I've added, the D option, decompress. LZJB is the decompression algorithm that seems to be used for all of the metadata that I've seen, but I'm not doing anything out of the ordinary with ZFS. I create a ZFS file system and use it. I don't change any flags or anything, so possibly you could get different compression here, but this should work regardless of the compression algorithm as long as ZFS supports the compression algorithm. And L size is the size after decompressing, which again is given to you by something you've done before this. Yes, if you want the modifications, you can obtain them where these question marks are. You could send me email, I guess, if you're interested. So we're going to basically start with the uberblock, find the data for a file. And we're going to go back and forth between ZDB and MDB to do this. And I'll go back to this large picture. By the way, this large picture and one other diagram, for some reason, is not in the printed conference proceedings. So I'm sure this is my fault, but I took a look and the pictures aren't there. So are these also going to be somehow? The slides will be on. Okay, so you can get the picture from here. Okay, so first thing I do is I make a copy of a file whose data I know, so that when I get to the end of this walk, I know I got the right thing because I'm going to see the data for this file. So I put the copy of the file, user dict words, into ZFS_FS, which is a ZFS file system / words, and I immediately dump out the uberblock for this file system, the current or active uberblock for this file system. And for those unfamiliar, the magic number here is uberblock. All right, well, okay. This is ZFS version 10. I don't care about the transaction ID. I let ZFS take care of that. The thing I want to get out of this is the root block pointer. And this says that the root block pointer is a pointer to data that when it's decompressed is going to be 400 hex bytes large. On the disk, it's 200 bytes. There are 3 copies of these. All 3, I think the 0 means which vdev the copy is on. 4E00 would be the location on the disk. It's not an exact location, but if you want that, go read the paper that comes with this. And the 200 at the end is the physical size on the disk. So what I'm going to do is take this block number, 4E00, and use zdb to get this data. And it's also, yes, it's little endian, for those who missed this, little endian and LZJB compression. So I basically take that 4E00 and run the modified ZDB and put the output into a file. We'll call it the metadnode file. So this is going to be the object set, objset phys-t data structure. And then I use my modified MDB on temp metadnode, and the metadnode file, all it contains is the decompressed objset phys-t. So I just : print it. And here it is. And it tells me, okay, at the beginning of the object phys-t is a metadnode, and it tells me the type is, it's a dnode, and gives me a bunch of other information. There's no indirection here. There's 3 what are called ditto blocks in the block pointer. So these are 3 different copies of the data on completely different locations on the disk. And when I did this print, I used -a to get the address of all the fields, and the block pointer is at location hex 40 in this temporary file. So what I'm going to do is use the location of the block pointer and use this : block pointer to get the block pointer for the MetaObject Set, the object phys-t. So this is going to take me now to the dnode array. And you can see here it tells you, okay, it's dnode array, it's a DMU dnode, and level 0 implies there's no indirection. If there was indirection, I have to do a bunch of other stuff. And we find that I've got 1 copy at location 1 copy at location 5000. On the disk, it's 800 hex bytes. Another copy at this location, 1C, blah, 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 and it's also 800 bytes. And a 3rd copy way out here on the disk, also 800 bytes. The logical size after decompression is hex 4000 bytes. And again, it tells me the physical size on the disk. So basically, I'm going to go to block number 5000 and dump out the dnode array. And this we're going to call the MOS. And I, again, put this into a temporary file. And once again, use MDB to look at the dnode array. And the size of one of these dnodes is 200 bytes. The data on the decompressed data is 4000 bytes. So basically, I've got 20 entries. So I should say 32 entries. So object ID 0 through 31 is in this array. If there's more object IDs, there has to be indirection, or the block size for this has to be larger. And so now what I do is basically I dump out all 32 entries and don't show you most of them. The first entry, the DN type is 0, so it is not in use. The second entry is something called an object directory. And what I'm going to do is basically go to the block pointer for the object directory dnode and dump out the block pointer using : block pointer. And this tells me, great, you've got an object directory. This is 200 bytes, logical and physical. It's not compressed. ZAP objects are not compressed. At least I haven't seen any compressed ZAP objects, but all the other data structures we're looking at are compressed. So basically what I'm going to do is go to location 200, and dump out the 200 hex bytes, which should be the object directory ZAP object. And to see that it's an object directory, I just dump out the first 64 bits, and this pattern, I'll put it this way, there's a header file which actually has this pattern, but this pattern, whenever I see it at the beginning, I know I've got what's called a ZAP object, actually a micro ZAP object. And I'm going to dump out the ZAP object, and one of the fields in the ZAP object is for the root data set, and it has a value. This is the object ID. So now I go back to the dnode array at entry number 2, the third element, and pick up the value that's there. So I'm going back to the dnode array, and the third element, the first element, element 0 would be at address 0, element 1 would be at address 200, element 2 is at address 400, that's the third element. So I dump that guy out. It tells me, okay, this is a DSL directory. It has a bonus buffer. The block pointer value is 0. It's not being used. So I'm going to go to the dump out the bonus buffer, which is at address. You can't really see it too well because, but it's down here. 4Z0 is where the bonus buffer is, and I dump out the bonus buffer for this, and it tells me the dataset object is at location 5, object ID 5. Back to the dnode array. Go and dump out object number 5 in the dnode array. And this tells me I've got a data set, and the bonus type is also for a data set. Again, the block pointer isn't being used, but now I go to the bonus buffer, which is at AC0, dump out the bonus buffer. This time there is a block pointer. Well, for me it was interesting because I figured it all out and I can do it. For the rest of you, sorry, but you have to take it. Okay, so B40 is where the block pointer is, and I dump that block pointer out, and again I get an object set. So I'm going to go back for a minute. So if you're trying to follow all this. Okay, so we basically just went, starting at the uberblock, we went object set, dnode array, the first dnode, went over, got the ZAP object, got the root dataset dnode, went down there, got the DSL dataset dnode, and now we're going to get this object set metadnode. And this is an object set for the file system as opposed to an object set for all of the object sets, which is the top object set phys-t. And go back here. Okay, and okay, so we've got a block pointer in the 5th dnode, actually the 6th dnode in the array, the object set array, the MetaObject Set array. And this guy has a block pointer. And again, I use blkptr, the D command, to dump out the block pointer. And it says it's a DMU object set. And down at the bottom here, I get this DMU object set, and I put it into root dataset metadnode, a temporary file again. So again, this guy is 200 bytes on the disk, hex 200 bytes on the disk, and 400 bytes in when it's decompressed. So I dump this out, and here is a second object set phys-t, a metadnode. Now this metadnode is for the file system. So if I had child file systems under this child data sets, I would have, each one would have its own object set phys and its own set of dnodes. So this is for the root of the file system. And one thing to note here is that there are 7 levels of indirection. So there are 7 levels of indirect blocks that you have to walk through to get to the next dnode array. And no, I am not going to show that here, in case anyone was worried too much. Okay, so basically though, the idea is you start with the block pointer here, and you dump out the block pointer, and then you keep dumping out block pointers and following in direction. And I think, is this where I put it? Okay, so here's a little description. So it says the block pointer basically shows 7 levels. And you basically do this sequence of going through each level, and I look always at entry 0 at each level because I want I want object ID 0, 1, 2. I want the beginning of the array, which is where the stuff is going to be that's specific to the root of the file system. And I keep going and doing this sequence of ZDB and MDB until I get a block pointer that says I'm at level 0. I've gone through all the indirection. Once I've done all the indirection, and see the paper at you have it. So here is the other picture that's missing from the paper, and this is just a little exercise of how do I actually get to a particular object ID. And the object ID I'm using here, 99F1D, happened to be for my large ZFS file system. And basically, you start with your object set phys_t for the file system. That's the second object set phys_t. You get the three block numbers that are in the 3 data virtual addresses. And thank you. And you start at the first one, and basically you work your way down, and I've got some information. So each one of these guys contains hex 80 entries for the indirect blocks. Now, that's based on a size of, I think, hex of 16K, uncompressed. There's actually a question I have, which I've asked and gotten the usual underwhelming response, which is if I have, okay, so these block numbers on the disk, the indirect blocks are compressed. If I have a 128K block size and I use the entire 128K on the disk and it's compressed, how many entries do I have after it's decompressed? And haven't gotten an answer. I'm trying to come up but one of the things I wanted to do when I'm doing this is come up with, well, how big can a file be based on the way this is organized? And the number I get, I think it was 2 to the, I can't remember if it was 2 to the 73rd or 2 to the 67th or 2 to the 68th. But that's the number I came up with, making an assumption that my blocks are all 16K large. So all these guys, it turns out, on the file systems I've looked at, all of them are 16K large when they're decompressed. And the bottom element, level 0, basically there's 32 dnodes in the array at the end, and I can take the object ID and just catch the low order 5 bits to get an index into this element at the bottom, and then I work my way back up. I shift by 5, and now each of these is hex 80, so I use a mask of 7F to get that index and work my way back up and up and up, and eventually I can follow all of this down and get to the dnode object that I want. Real simple, yeah. Okay. So here we are. I've done the walk. I'm not showing it. Go read the paper. I've done the walk, and I'm at the end, and I'm at level 0. And again, it tells me it's DMU dnode. This is a dnode array. I dump out this guy into a file and dump this out. I get the master dnode, which is the second entry, and the block pointer, which again, this is going to be for a ZAP object. I dump out the ZAP object, and I look for an entry whose name is root. And this is object ID 3 in the second array of dnodes, the file system array of dnodes. So now I go to that object, dump it out, and this tells me, okay, I've got a bonus buffer which contains a znode. The type of this is a directory contents. The ZAP object will contain the directory contents. So now I dump out the znode so you can take a look at it, and then the block pointer from the root directory dnode, and this is again a ZAP object, and the file that I'm looking for in the ZAP object is the words file. It's at object ID 15, or 21 if you prefer. And now I go to that dnode, dump it out. It's plain file contents. There's one layer of indirection. The user-dict words file is 266,367 bytes or something like that. So it's larger than 128K. So we have one level of indirection. And I dump out the block pointer at 2A40 and dump out the first block. And this again, this is an indirect block, so this is going to be another block pointer. And this time I'm at level 0. It's a plain file, so if I go to this disk location, A220000 for 128K, and dump it out, there's user-dict words. Piece of cake. Yeah, well, you know, when I've done the dry runs, a couple of times I've basically skipped all the MDB and just said, okay, you start here and here. You get it, but okay, so what does a mirror look like? Well, mirrors are just copies. So basically, you take any block number and you can go to either one. The main difference here is that you'll notice with the ZDB, I use 0.0. That'll refer to the side 1 of the mirror, the first side. 0.1 would be the second side. If it was a three-way mirror, 0.2 would be the third. But everything is the same. They're complete identical copies as far as I can tell. And no, I didn't sit there and go through it all, but I got far enough to say, you know, this is matching what I'm seeing without a mirror. For child data sets, only difference here is one of the MetaObject Set entries is for a directory child map, and here's a child data set. In other words, if you will, a mount point under a ZFS mount point. And again, this takes me to DSL DIRFIZ data set. And again, I get an object set for the child file system, a master node in the child file system, and then all the other dnodes. And snapshots, just a different object in the MetaObject Set array. Where what happens here, what seems to happen here is that unchanged data and metadata should be the same as when the snapshot took place. And in fact, it should be the same as the original file system that you're snapshotting. So we don't actually copy stuff here until things get changed. It's all copy on write. And okay, so I'm almost at the end because I've got a guy up here who's holding up a sign that says 5, 4, 3, 2, 1. I guess those are minutes, right? Okay, so some conclusions. The tools are a bit clumsy. I've had several people say, oh, this should be done in ZDB. My view on ZDB is it's very much like FS type, for those familiar with it. FS type, type FS type, and it gives you one line. Type FS type minus V, and it gives you 50 pages. And ZDB is very much like this. You type ZDB minus D, and it gives you a couple lines. ZDB minus 8 Ds. And I did this a couple months ago. It hasn't finished yet, as far as I know. So it gives you everything. And actually, ZDB does give you everything, it turns out. It's just that I didn't understand what it was showing me. You do this walk and well, at least I got a better appreciation of what, not only what ZDB is telling me, but also the on-disk format specification is actually telling you everything. That paper actually is complete. It's just, I didn't understand it. It's one other problem with ZDB is it's not interactive. And for something that allows me to debug, I want something that's interactive. MDB, the problem I have with MDB is it doesn't do the decompression. And I played with this for a while. I changed MDB to have a dprint or a zprint command that you specified decompression, but this was really clumsy. I was actually in MDB doing a fork and execing another copy of MDB to look at a temporary file. So not maybe the best way to do it, but I actually have a much better idea of what I want now, and maybe I'll get around to writing an RFE, except that this already does what I need. But it may not be enough for someone who's trying to actually debug the file system that doesn't have any bugs. Okay, so yes. One other thing I notice is that if you take a look at the block numbers, and the paper actually has a table at the very end, if you look at the block numbers that are being used for all the metadata, they're all really close together. So it looks really bad. You've got this block, and then you've got it here, and then here. But if you take a look at the numbers, the actual locations, 2 reads, and you've pretty much got all the metadata. They're all the data is close together, and partly that may be due to compression. But all the data is close together, so it's not as bad as it might seem. Yeah, I'd like to be able to load specific CTF modules. Doing the walk for the structures on an open file actually turns out to be more difficult. Because for an open file, I can find a Z node, but the D node, I know how to get to the D node, but I don't know how the system is doing it, because the way I do it is I walk a linked list of all the D nodes for a particular file system. So if you had 1 million files, you'd be walking a linked list that's 1 million entries long, and I can't believe the system does it this way. Let's hope not. Yeah, let's hope it doesn't walk a 1 million entry linked list. So, okay, so references. Actually, this is not as complete as I'd like. There's a description of space maps by Jeff Bonwick that you can find on his blog, which I don't talk about space maps, but you'll run into them if you tried to look at this stuff. There's a couple descriptions of things like copy on write that are quite good, but again, when I was doing the slides, I didn't have time to look for my references. And the source code, in particular, the ZDB source code. ZDB is pretty interesting. It actually uses most of the kernel code. So, I mean, if it's a debugger and there's bugs in the kernel code, well, you're using them to do the debugging, but that may or may not be important. So, and